Welcome back to the session. Those of you who have attended, who have joined us a little late, for your reference, I will upload this slide deck back for your reference, and you can go to the YouTube and search for these YouTube videos and go through it, and you can get up to speed on what you perhaps missed out on. Uh, the key message is another software, another user interface, but similar results. And I wanted you to get a feel of it at this point of time. The key message I want you to remember is that pretty much similar features are there, and and uh, uh, I believe that for rooftop and most CNI installations, Solar Labs is actually very functional and gives you a lot more advantages. If you went through the PVSys demo, you would realize it doesn't give you the heat maps, it doesn't give you the near and far shading analysis the way you got it in Solar Labs or Helioscope. Uh, it has uh, added some modules for giving you ROI and things like that. Those are all features which can be quickly adapted to in the Solar Labs. And really speaking, these are the strengths and weaknesses of different products. Also, PVSys being a foreign software is far more expensive when you go for a legal copy, and it will not give you the features you're getting in Helioscope or Solar Lab until unless you add a separate CAD application. So if you take a look at this, the second software that I'll cover later in the day today will be SketchUp with Scallion, which will have excellent CAD features because it's primarily a CAD application, especially designed with a plugin for solar. That's plugin is called the Scallion, and it gives you a very good site design, but then it lacks the detailed reports that you could get from a PVSys sort of an application. And Helioscope is a third software which we'll cover later in the day, which does an interesting, execution and is very functional. And Solar Labs is something like Helioscope, but an Indian version of it. So solar PV system design, today I'm going to cover the basics of design for residential spaces, actually for rooftops. And we will cover, different types of solar setups, and we'll actually do the design and calculations for it. So this is the meat of it. I'm glad everybody is here, and we can go ahead with it. So we are all aware of the power of the sun. I mean, we are getting on our Earth approximately 1000 watt per meter square of solar energy, and that's huge as an opportunity for our world. Uh, if you take an example of 50 square meter of a roof area, okay, for 4 hours, that's actually 200 kilowatts of energy that can be farmed from it. So can we farm? Do we actually farm 200 kilowatts? I have a 500 square yard house. Do I actually get 500 kilowatt of energy out of it? No, not really, because my actual roof area might be around 2000 square feet or 200 square yard construction, and therefore it will actually, should I get 200 square yard to 200 kilowatt out of it? Actually, no, because I won't put panel back to back on the entire roof. I'll actually be having gaps between various panel strings, and therefore that is going to again reduce the available energy that I can farm out of my roof. And then of course, why don't I get for all the panels that I'm putting up this energy out? The answer is the efficiency conversion. The conversion efficiency is anything between 15 to 20% of the light, which is of the energy that is falling on the module. So because of the module efficiency issues, you may actually get a fraction of the total energy converted into electric energy. And then it will have to go through all sort of other losses. There will be soiling losses, there will be losses in the string or the wire, there will be losses at the inverter. So the actual final energy that you are going to use will be a very small, a relatively small, smaller fraction of the total energy that is available to you. Irrespective, the potential for solar is phenomenal. I mean, just solar, if you compare with all the energy sources available to humanity as of now, all of these little bubbles are the estimated energy opportunity from different, energy sources like coal or uranium or wind. But solar, just this curve, this pi that is there, this quadrant that is there of a whole circle, that is the that is how big solar is with respect to the other sources of energy. So it is almost unlimited. It is safe. It is clean. Okay, and all of these are actually under apostrophes, because uh, when you say safe, but remember it creates DC voltage, and DC voltage beyond 30 volts can be fatal. Okay, so you have to be very careful in handling the solar PV circuits. It is clean, yeah, but then it's always been debated that modules are created in processes which take huge energy. So it is not absolutely clean, but it's definitely cleaner than a lot of other sources. And farming itself is not going to generate any additional fossilized carbon emission for the world. So if you take a look at it, it has a lot of advantages. And what are the disadvantages? It's high initial cost, the fact that it is weather dependent, and if you really want to ride, the 24-hour cycles and the weather's vagaries, you need to have energy storage, and energy storage can be very expensive. A 200 mAh Exide battery can cost you anything between 18 to 20,000 rupees. So it is an expensive proposition. So how do solar panels actually convert solar energy to electrical energy? We all know that primarily it triggers an electron when it strikes a PV junction, and through appropriate design of our module, we try and trigger a current, which is going to be used for farming the electric energy. The different types of solar panels that are available, they are in technology terms, you have the crystalline silicon, you have the thin film, you even have the extreme end, the gallium nitride solar cells, which are actually the ones which will give you the highest solar efficiency. They can give you up to 30% solar efficiencies, but then they are so expensive, they can only be used for niche applications and strategic applications or in space applications. And then you have in crystalline silicon, you have a range of modules. There are the monocrystalline modules, and there are the polycrystalline modules. And the monocrystalline modules, you can simply recognize them because they are dark. They are far more efficient in their capacity to trap energy as compared to polycrystalline. So monocrystalline will typically be very dark. Okay, it just doesn't let that light escape out. Polycrystalline, on the other hand, will be slightly bluish in color when you take a look at it. Also, one of the simplest way to recognize a mono versus a poly architecture is, if you take a look at a mono panel, you will see these round black spots. If you take a look at it, can you see these uh, uh, corners? So it is actually, when you look from a distance, they will appear round. Okay. If you take a look at a typical panel, it seems dark, and you see these round corners there. It is a monocrystalline panel. And if you see a straight line design, it is likely to be a polycrystalline. And then, of course, you have other technologies like thin films, which came with a philosophy that, in a typical silicon-based panel, you are actually generating the energy from a very small amount of silicon. So they said, let us look at, instead of wasting silicon, which at a point of time was very costly, it used to cost $300 a kg a decade plus back. So they said that let's actually create a thin film of silicon on a substrate which is inexpensive and use that for farming solar energy. And they did farm solar energy out of it. Those technologies were the start of the amorphous silicon panel, and the amorphous silicon panel gave PV effect, but at a lower efficiency. Okay, so there was a trade-off on cost of silicon with efficiency, and over a period of time, as crystalline silicon costs came down, it actually put a tremendous pressure on the thin film technology, which is a very small share of the overall, solar PV module market now. If you take a look at it, the cost trend on this, a decade plus back, the cost of crystalline silicon was $300 a kg. In May 2011, it was $75 a kg. In 6 months after that, it crashed from $75 a kg. It came down to about $35 a kg. Then it continued its spiral down. In 1.5 years, that means somewhere by 2013 start, it was actually trading around $18 a kg. It remained around $18 a kg, for nearly 3 years or so,
Uh,
4 years or
Doc-
so. And
Dr.
in
Ashwini,
2017,
Ashwini, I'm sorry to interrupt,
yeah,
but your presentation has perhaps got stuck up. We're not able to see the next slide. Perhaps you're trying to show some slides related to trends of the cost of silicon, but that slide got stuck up only on the comparison slide of this monocrystalline and polycrystalline silicon slide.
oh, then it is okay because I have not moved the slide.
Okay, that's fine. That's
I
okay.
have not
Thank
moved
you.
the slide. Sorry.
Thank you.
I must go back to it.
No, I'm
Uh,
sorry.
no, it's okay. So I have not moved on that slide. I'm just giving you a discourse on the way the pricing has moved. And the way the pricing has moved is crazy. So in 2016, and it started moving again from 18 and a half, it started, came down to 16. And there were clear visibility that there was dumping that is going to take place because the markets were shaking. In fact, it came down to $12 a kg. So you can just imagine the pressures that were there in the ecosystem as the prices started crashing. They said it would touch $10 a kg. It touched $10 a kg. It went below. It is somewhere, around $9 a kg right now. And you can just imagine if, prices crash like that, how the entire ecosystem will shake. So when people are planning only on the thin films and, the other technology crashes, prices like this, the market shift. So crystalline silicons actually been capturing most of the market because of the way it has been going. And after all, it is silicon. It is sand. It is around us everywhere. That is actually getting processed in making these panels. Then, of course, there are other equipment. You have beyond modules. You have the inverters. You have the solar charge controllers if you are actually charging batteries. Then there are inverters which could have charge controller functionality built into it. Okay, so it's pretty wide range of material that is available, components that is available in the marketplace. You have also got things like you have the conventional lead acid batteries. You also have lithium ion batteries, and then you have the structures. You have the cables, the mounting accessories. The connections are done with what is known as the MPC4 connectors. You have a whole lot of little components that actually complete the balancer system. You have your distribution boards, circuit breakers, surge protectors, overcharge protection devices. So we will have to look at this entire gamut, and we'll be covering that in the next few minutes. So we are typically covering three types of SPV systems today. One is the on-grid or grid-tied design, and this design is actually the most common. It is the one which actually gives you the fastest return on investment because it doesn't have a battery. You just feed your energy that you generate back into the grid, and as long as grid is operational, it will be operating. And if the grid is not, if the grid goes down, if there is a blackout from the grid side, the grid tie solar PV will shut down. Okay, the grid tie solar PV will shut down. This is because it must have what is called the islanding, anti-islanding capability. It cannot be an island of power generation on its own into the grid, because if the net is shut down by the distribution company, if the power is shut down by the distribution company, it could be for conducting some repair. And if there are islands of power generation on it, it can electrocute the electrician who is working on the grid. So a grid tie system will work only if there is power from the grid. But when it does it, it takes your solar energy that is generated, and it will, in a net metering arrangement, only charge you for what is the differential energy that is consumed by you. And since you're generating energy at zero rate, but the rate at which you are paying the distribution company was 7.5 rupees or 8 rupees, or in Bombay it can be as much as 10 or 12 rupees depending on the nature of your site. You can just imagine the pace at which you can get your payback from a grid tie SPV system. The second class of SPV design is for an off-grid system, where you say that I do not have any electricity from the grid, and I'm going to generate my own electricity from sun, and I'm going to harvest it and store it and use it. Okay, and this will require a battery back definitely, and we will cover the design elements of it later in the session. And then you have the hybrid one, which is technically the most complex. It's a combination of both the on-grid and the off-grid configurations. And the system is connected to the electricity, but it also has a battery backup for energy storage. So it is also expensive. It's a little more complicated to design and use. And well, we'll cover briefly this one also. As of now, hybrid is not that common, and sometimes we use hybrid with a little more, rigid definitions. This is a loose definition of hybrid, and we'll cover that when we come into the that particular section. So this is how a typical on-grid solar PV system design looks like. You have the panels here. Okay, so if you can see, you have the panels, and these are connected by the DC isolator, which is actually an on-off switch. You off it, and it will isolate the panels. It will not let that energy come into the side of the circuit. And then you have a distribution board, which is having a surge protection device or an overcharge protection device, and you have the circuit breakers. And then this DC current that is generated from the solar PV is going into an on-grid inverter, and the on-grid inverter is creating AC power at its output, which is going through a distribution board. Okay, the circuit breakers and surge protection devices and an on-off switch here into the main panel. Okay, and you will normally have a net metering device here somewhere, which will measure the energy which is coming in from your system and the energy which is coming in from the utility, and the differential going into the load. Okay, so this is a typical on-grid system design. And as mentioned, the on-grid system is still connected to the electric grid. It is the cheapest setup. It has just two main components, which is the solar panels and the inverter, and the energy demand is complemented by the electric grid. They call this, it will not function during a blackout. Okay, it will not function during a blackout for safety reasons, because of what is known as anti-islanding requirement of your on-grid system. It cannot be an island of power on its own into the grid, because that can create fatal implications in the grid. The off-grid system is looking similar, but if you take a look at it, it's slightly different. The solar PV panel generating energy, the isolator, the circuit distribution board with the circuit breakers and surge protection devices, feeding into a solar charge controller, which is charging a battery bank. And the purpose of the solar charging controller is to make sure that you don't overcharge the batteries and you don't undercharge the batteries. Okay, and these charged batteries are feeding the inverter. Okay, it is feeding the inverter through overcharge protection device, the DC circuit board, overcharge the OCPDs. Okay, and again there is an output of the inverter going into an AC circuit board or an AC distribution box, to which the different load circuits are connected. Okay, so that is a typical off-grid system design, and it consists of four different components. The two new components here are the solar charge controller and the battery bank. Okay, and it requires batteries for storage, and the batteries can be very costly. Okay, it can be as costly as the rest of your system, and batteries have a very short lifespan. Okay, if you're using lead acid batteries, they'll not have a lifespan of more than 3 to 5 years. So you have to actually realize that the moment you go to off-grid, your ROI starts plummeting. Okay, off-grid is still feasible in some areas where the main grid is not there, and it is more economical to go for these sources of power. But otherwise, if you actually start looking at it, people would normally not look at an off-grid in typical cities. Then you have the hybrid systems, and let's take a look at it. The input circuit is practically the same. You have the panels feeding into an isolator. You have the distribution board for the DC distribution board, and that takes the connection, the input into the inverter. It's a hybrid inverter. It is charging your batteries. There is an output going out, okay, which is it's taking the input from the utility also, and there is an output which is going to an automatic transmission switch. Okay, now this ATS can actually be built into the hybrid inverter also in some hybrid inverters. What the ATS does is it gives the logic by which the load, this external load, it gives a logic by which this external load is going to get the power. It will say that my first preference for the power is going to be from the battery. Okay, and then if the battery is not having enough power in it, then I will take energy from, say, the PV panel. Or if there was a provision to attach another source of power like a DG set into it, I'll take the next thing from the utility, and if the utility power is not there, then I'll take it from the DG set. Okay, so you can just imagine how this logics could go, and it would depend a lot on the sort of inverter you have there. Okay, but this is conceptually how you're looking at a hybrid system design. Hybrid system design, sometimes you also use a different software for designing it. That's called Homer, but that's again a different chapter altogether. And Homer stands for hybrid optimization of energy renewables. Okay, and the Homer is and hybrid. Actually, strictly speaking, when we say hybrid, we're talking of beyond just solar. Okay, beyond solar and utility, there has to be another type of energy system there also, like DG set or a wind system, or a tidal energy system. Okay, and that's how you actually take hybrid. So we are using a very simplistic use of hybrid in this definition. So now we are getting on to the third step. The third step is actually doing an on-grid system design and calculations. We are going to look into what were the steps which are being done to design this SPV system. You saw some of it being done by the software, okay, but we don't know the full logic of the software, and sometimes you want to actually do this on your own also. Remember what the software did? Software in the solar labs took the entire roof Okay, wherever you laid the section, and it designed the it designed the panels for the entire rooftop. Sometimes you don't want to do that. Sometimes you want to go by other thumb rules which is designed for your rooftop. For example, you can say, I want to design for my rooftop based on my load. Okay, so you analyze your load, your actual consumption requirement, and you say, for this, I need my panels. So the roof can give you, as I said, maybe 200 kilowatt, 100 kilowatt, or 50 kilowatt conceptually. But you do an analysis, and actually, when you do the the Solar Labs or Helioscope sort of design, you'll find that that roof is actually only usable for 10 kilowatts. Okay, but you may turn around and say, I want it for my load, and my load is only 6 kilowatts. So I don't want to create for 10 kilowatts of panels. Okay, so you do a load analysis. You can also get limited by the budget of the customer. Budget says, I'm only going to pay for a 5 kilowatt. At this stage, just give me a 5 kilowatt. Let me see this work. Maybe I'll add another 5 kilowatts later on. Okay, so these are some of the different real life scenarios that can evolve. So you do need manual design, okay, to add on to the solar design in real life, and you do the load analysis, and you size your panels, and then you size your inverter, and then you design the elements of the rest of your circuit, and we'll go through a quick view of how that is done. So load analysis is simple. One of the simplest way to do the load analysis is you take your monthly bill from your utility and divide it by 30 days. Okay, so if your monthly bill is of 600 units, your in a city like Faridabad, where I'm based, that means I'm getting a bill of around 4,500 rupees or 5,000 rupees. Then very clearly, my daily bill, my daily consumption is 20 units. In this example I have taken, its monthly consumption as 170 kilowatt, and when I divide by 30, I get a daily consumption of 5.67 kilowatt hours per day. Okay, now how do you do your panel sizing? Very simple. You know that daily consumption is 5.6 kilowatt per hour, kilowatt hour, and you know that in a typical uh, North India's location, your sun peak hours are around 5 hours. 5 hours when you are going to get about 1000 watt per square meter energy out of 24 hours. Okay, so this is a thumb rule. Okay, if you take this thumb rule, what it means is divide 5.67 by 5. Okay, and account for 30% of your losses. So once you do that, your PV panels should be 5.67 by 5 and multiplied by a factor of 30%. So you get about 1.475 kilowatt as your required rating for your PV system. And since you know, let us say we have selected a panel with a wattage rating, power rating of 380 watt. This is going to be 3.88 panels. So you'll select the next higher integer, which is 4. So you need 4 panels of 380 watts to be able to deliver the power requirement that you have. So that is how you do your PV panel sizing. Okay, and when you have to come to the PV inverter, you know your PV power. Okay, you know the PV power. And typically you multiply this up by actually say 20%, 25%, and select a inverter with a power rating which is greater than the power rating of your input PV. Okay, so we have said the first step is that it should have a power rating which is greater than the power rating of your PV panels. Okay, and this is giving you, we have taken the next higher size, which is say 2 kilowatt or 2200 watt, 2.2 kilowatt, whatever, and we have taken selected as an inverter based that. But then there is a second thing we have to do. What is the maximum voltage that the inverter can take? And what is the maximum input current it can take? Okay, there are other considerations also, but we'll come to it later. But maximum VOC is 400 volt. If you take your 4 PV modules and you have put it out in one string, okay, so you know that the voltages will add up, the current will remain same, but the voltage will add up, and therefore the voltage of the PV array maximum voltage is going to be 195 volt, which is less than the maximum voltage that is taken by the inverter, which is 400 volt. So it is safe to connect this inverter to the to this particular array. And of course, the input short current is another requirement. So we know that the input short current from the modules is 9.94 ampere, and the maximum input current that the inverter will take is 10 ampere, so we are safe. So we sort of take this as an acceptable inverter for it. Okay, sometimes you have other considerations, like what is the minimum uh, voltage input that has to be there to the inverter for it to work. Okay, so that you take a look at your specific product and take that design. We'll come back to it from another perspective in a later part of the slide. Okay, later part of this presentation. But you're getting the first part basis for designing your PV circuit and selecting your inverter. Now we're going to select the rest of the elements of this circuit. So what have we done? We started here, consumption of the load. Okay, that is 5.67 kilometer per hour. We designed our panel. Okay, 4 panels, 380 watt, connected in series. Okay, we selected our inverter. We said it is a 2200 watt inverter with a VOC of 400 volt and maximum input of 10 amperes. So now let us go to our DC distribution board and circuitry. Isolator is a simple on-off switch, okay, except that it will trip both sides together. Okay, it is not a switch where you just take off, break one side of the circuit. Okay, and we take a look at, so it's a 2-pole isolator. And when you take a look at our overcharge protection devices, or you have a surge protection device, and you will have, maybe you will add in your distribution board RCCB, which is a residual current circuit breaker, and you will also have a DC circuit breaker. And how do you calculate the DC circuit breaker rating? You know your current rating from the module is 9.94 ampere, and there is only one string. If there are multiple strings, you know the current will add up. Okay, so you take your ISC, multiply it with the number of strings, and then multiply it by 25% more as your protection limits. So your circuit breaker rating should not be less than 12.425 ampere. Okay, so what we have done is we have selected a 14 ampere, okay, 2-pole DC circuit breaker. Okay, so this is how a circuit breaker rating has been computed. Okay, and when we are looking at our output circuit is determined by your inverter output is 2200 volt, but your output voltage is 220. So your AC current here is 10 ampere. Okay, and you again provide for a buffer of say 20-25% or whatever, and you plan for at least a 1280 2-pole AC circuit breaker. Okay, so this is how you plan your output distribution board, and you have now got the basic design for the solar PV circuit. Okay, so this is covering your SPV design for on-grid. The off-grid system design is, Rachit, you are there? Rachit, you are there in the group, I see.
Yes, yes, Mr. Dr. Shoni, I'm here.
So the question which is there is what all is not there in your software?
Yeah. So basically, in our software, like Dr. Ashwini said in the starting, that you can only design a on-grid system. Okay. And since we are talking in terms of on-grid only, so in on-grid system, you can do pretty much everything, right? So like coming to stringing portion, right? So as of now, you won't be able to create SLDs, that is single light diagrams. So you will be able to create them manually. Okay. So but like most of the software, our software is AI based, right? So it automate everything. But coming to the SLD, that portion is still in the manual phase, right? Then coming to the detailed designing phase, right? So right now what we provide is we provide you with a preliminary proposal. Okay. But we have like upgraded this, so we have bought in a like add-on kind of thing which we called a detailed designing segment of ours, in which you will be able to do string sizing, cable curling, right? Your SLD will be automated, right? So these three things are one which you are unable to do as of now, but they are in the system, but they will be as an add-on, right?
So, for example, so this is just to give you an idea why you must know a little about the manual designing. Okay,
Right.
and there is no rocket science to it, friends. It is as simple a circuit design as this. That's not going to change. Okay, you're just going to add these little elements up, and you have to know how you have to do it to be able to configure it. Uh, you do get that convenience. For example, a software like Helioscope will give you a SLD, which is a standard SLD like this, on which they put the the final figures and say this is the final SLD design that has come out of it. But it's the same SLD with just these figures being put up on it. So as long as you can take care of it, you don't need to actually worry about the output. And in fact, I'll be advising Siddharth at Solar Labs that it is as simple as just letting one slide come out with these results. You might as well add it to your software at a point of time. Okay,
Sorry to interrupt you in between, Dr. Ashwini. We have that.
okay. So
We
if you have
already
it,
have that.
yeah.
Yeah, yeah.
So
That's what I was saying, that we have that, but it's in the manual phase. Okay.
okay,
It's not
okay,
automated. See, what happens that when you do all these things as SLD, so even if you create it out of Helioscope, you have to edit in AutoCAD. Okay, because when we go to actual actual installation, the SLD always changes. Okay, so you have to make changes again and again by just taking the export to AutoCAD, right? So that is what we also provide, that our SLD will be generated in our software as well. Okay, it will be manual. All you need to do is, if you want to make any changes to it, then you have to export it to AutoCAD and then you can make the changes.
so we have got a feel now of how the software works, where its strengths and limitations are, and how you will actually do the design anyway. And as you can see, it's not too difficult. It can be a good way to check your design, to fine tune it in the field conditions. And as I cover elsewhere, an actual solar PV engineer is a lot more than just a designer or an electrical engineer or a mechanical engineer or a civil engineer. He's actually all of these. So everybody needs to understand some of these fundamentals as they go into the field for a SPV deployment. So we now come to the off-grid system design. Okay, off-grid circuit, you recall this is a circuit we had shared. You have to go through the same steps. You have to do a load analysis. You have to do a sizing of the solar panel. Then after that, you size your battery bank, and then you size your inverter. Okay, and this is how you actually do the full thing. Now I'm trying to do a slightly different version of a load analysis. One of the simplest way is that if you are trying to take a grid connected site to an off grid condition, then you would actually just take the bill and use that to calculate what is your average load. But if it is really a site which was never having any electricity and now you're going to put electricity there, then you'll do the load analysis. Okay, so you'll make a chart which will be a worksheet, which will be listing all the equipment you're going to run off that particular power source, and you will put power for each of these elements and the number of quantity of each of the elements and calculate the total power and how long that particular device is going to be used to calculate the total power consumption in watt hours. So I've filled it out with something. Okay, and it gives me that I will have a consumption of 5 kilowatt hour per day for my this particular home, which has 9 lights, one LED TV, sorry, 4 lights, one LED TV, 2 electric fans, fridge, a laptop, and a washing machine. Okay, and well, you know the total consumption, so you can do the sizing of the panels. And you go by the same logic as before, and you find that you need 4 panels, and that you can actually connect these 4 panels in a string, and that you are looking at the sizing of the battery bank. Okay, so the battery bank, now this is something that you need to take a look at it. Okay, the battery bank is determined by your daily consumption. It must meet your daily consumption. Okay, by the depth of discharge. Okay, so by the depth of discharge. So your depth of discharge is linked to the battery type that you have. Lead acid battery will get damaged, if it is discharged beyond 80% of the total battery capacity. In fact, the life of the battery starts getting impacted if it is discharged beyond 50%. Okay, so a lot of times you will have a depth of discharge rating that you will say is 0.5. Okay, and the efficiency of the system, you factor that at 85%. And you have thumb rules for the system voltage. So you say that for small voltages, your small installation, as you are going to have a system voltage of 12 volt. For medium size installations, you will have 48, 24 volt. And for large installations, this is given in the lower corner here, large installations, you can have 48 volt. And then very large voltages, large sites, you can even have 96 volt or 120 volt designs. Okay, but let us say we have taken 48 volt. Okay, if you take this at 48 volt, you are talking of a battery bank capacity in ampere hours of 245.7 ampere hour. Okay, what we are doing is we are selecting a battery rating of 250 ampere hours, or we can select 2 batteries of rating of 150 ampere hour each. That's another option. Okay, but number of strings that you will have is battery capacity by battery rating. You have 1. Okay, number of series of these batteries that you will put up, because you are looking at 48 volts, you will have 4 batteries. Okay, so 4 batteries, number of string equal to 1, 4 batteries, and this is how you're configuring your battery bank. The other additional thing you might want to do is what is your autonomy? Okay, how many days of battery backup do you want? We have just kept it as 1 day. We take a look at it, we have kept it as 1 day. Okay, but and that is adequate. But sometimes you may want to plan for more, then your battery backup requirement will go up. So sizing the inverter to account for the surge power motor loads. Now this is something very interesting. We multiplied, in my design of the inverter in the previous round, when I said that your actual rating was coming to 1.5 kilowatt in this, I said, take a look at this slide. In this slide, I said that this is 1.5 is your maximum power. I said normally you'll multiply it by 20% or whatever, and then take the next higher inverter rating. So why do you do that? You do that because of the surge power that is there in a typical site. So if you have a washing machine, okay, or if you have a fridge where there is a motor load, then there is an inductive power drawn at the start of the machine, and then in the inductive power, the power needed is much more. So because of the startup load that is there, typically you factor it like this. For lighter devices like TVs or LED lights or laptops, you provide for a 30% factor. But for devices like washing machines, fridges and fans, your inductive load can be much higher. So you provide for a higher power requirement in sizing your inverter. And here, as you can see, your inverter sizing is getting bumped up to minimum 2 kilowatt, and therefore you select the next higher rating of the off-grid inverter, which in this case we have taken as 3 kilowatt. Okay, and that is how you select your off-grid inverter specifications. Then you go for a solar charge controller. Okay, now your next step is to design your solar charge controller, and you know that you have a battery in series which is 48. Your VOC is 48.8 volt. Okay, uh, you know your current ratings, you know your voltage ratings, and based on that you select a solar charge controller. We have selected a solar charge controller of rating of 200 volts and ICC of 50 amp, and it is safe. It can be used with your PV panel and your battery system. Okay, and what we have done now is we are looking at the circuit. We are looking at the circuit. We have designed the big elements of it. We have defined the load. We have defined the PV array. We have defined our battery bank system. Okay, and we have defined the solar charge controller. So now we will define the other elements, which is the DC circuit board, the DC input DC circuit, the charging circuit, and the AC circuit. And let's quickly look at it. The input DC is the same calculation as before. Okay, and it is going to end up with a 1480 2-pole DC circuit breaker here. Okay, and this is feeding into the solar charge controller, and the second DC circuit breaker that is there, again it is taking the same current, so it has the same specification of the circuit breaker. But if you come to your battery bank output, okay, so here your output is 3 kilowatt voltage and power rating, and input is 48 volt. So your IOC here is 62.5 ampere. So the rating for this circuit breaker is 70 amp, okay, minimum. So we have taken 70 amp 2-pole circuit breaker at this place. And here it is, the output is 3 kilovolt and the output voltage is 220 volt. So divide it and you get 13.64 amperes. So we select the next high rating for this circuit breaker, and that is a 15 ampere 2-pole circuit breaker. So this is the way you have designed the elements of your distribution board. Okay, so we'll come back and look at some of the things that we have not touched. We have not touched the issues on the temperature variations and on the wiring selection, but we'll come back to it separately. And now we are looking at the solar power system. Okay, basic calculation and design, and the steps here are, as we covered before, load analysis, then sizing of the solar PV panel, the sizing of the inverter, and the sizing of the battery bank. So pretty much similar steps, but you don't have a solar charge controller. It is all built into the hybrid inverter. The load analysis is the same. Okay, PV panel sizing is the same. PV inverter is also pretty much a similar logic. Okay, and you select it as before. You look at carefully making sure that your voltage and current rating output of your DC is matched by the input of your inverter. Okay, and that's how you are ensuring that the system is safe and will not blow out or trip. Tripping typically is if it is under fed with the voltage. Okay, now you're coming into your load analysis for the battery bank sizing. Okay, so you calculate your power consumption, and then on the power consumption, you size your battery bank in a similar way. Okay, and then you are actually getting into your hybrid system design, and you take a look at it. It's practically the same logic which is going to flow through. The input DC circuit is a 14 ampere two-pole circuit breaker. The uh, uh, the battery bank is calculated as the 3K kilowatt inverter rating and the 48 volt battery bank rating. So it's a 70 ampere two-pole circuit breaker. The output AC circuit breaker is 3000 volt wattage by 220 volt. So it's a 14 ampere two-pole circuit breaker that has been taken here. So this is how you have done your distribution board selection. So how does the temperature affect the string size? Now this is also something you can't really ignore. Okay, for example, you know that the modules are rated to give a particular power at the standard test conditions. And the standard test conditions are conditions of 25 degrees centigrade, okay, at an air mass of 1.5 air mass rating, okay, at zero wind condition. Okay, now if you go into areas like Chandigarh, you will have winters can be quite cold, or in Ladakh, winters can be really cold. Okay, so as temperature falls below standard test conditions, your voltage increases. Okay, as it becomes brighter, your current increases. Okay, so if the temperature is falling and your voltage is increasing, you have a negative temperature coefficient, which is typically for every 3 degrees. The thumb rule for a crystalline silicon module is for every 3 degree rise in temperature, there is a 1% fall in the voltage generated. Okay, so VOC will fall by 1% for every 3 degree rise in temperature, or reverse way, every 3 degree reduction in temperature will increase your voltage VOC by 1%. Okay, so let us now take a look at an example. You have a cold temperature of 15 degrees centigrade, minus 15 degrees centigrade. That means you are 40 degree below your standard test condition. The module was rated at 35 volt on standard test conditions. Your inverter maximum input voltage was 600 volts. Okay, what is the maximum number of modules that you can connect in a string? So what you do is you take that delta of 40 and find out what is the percentage increase in voltage. It is 0.132, okay, or 13.2% increase in voltage, which means that the VOC of 35 will rise to 39.62 voltage. Divide 600 by 39.62, you get 15.14. You don't want to go to 16. The moment you go to 16, you will risk crossing the input voltage. So you'll select the next lower level, which is 15. Okay, and question to Rachid, do you factor this in your design software?
Yes, sir, we do.
What temperature range?
Sir, like you have to mention the temperature range from like for example, what we do is that we take the weather data set in accordance, right? So for example, like in this case, we take STC conditions at 25 degrees Celsius. So suppose like you take the example of Chandigarh, right? So in summers, Chandigarh is very hot, right? So the weather data set of that area, right, in that region will be taken into accordance. So you don't have like you won't be able to enter it manually, the system will calculate it automatically.
Okay, so some point of time I will study that a little more, but taking you on your word. But guys, you're getting to see what this means. You have uh, actually you can factor this in to define the maximum string that you can actually attach to in your PV system that you can configure in your PV system. Okay, there is a minimum number also that is relevant. Okay, so when you are, uh, if your temperature goes up, you have put the system in Jodhpur. Okay, and in Jodhpur, the temperature goes up to 45 degrees centigrade or 48 degrees centigrade, say. Okay, in summer. Now, when the temperature goes up, your VOC will fall. And if your voltage generated from your PV string falls below the minimum required for the inverter, the inverter will trip. It will not work. Okay, so you have to make sure that your PV system must also give the minimum number of modules for the inverter to function. Okay, and the module temperature is relevant. It is not the ambient temperature. Ambient temperature in Jodhpur is 48, but the module will heat up a lot more at the junction, and it could be at 70 degrees centigrade. That's the example I've taken. Okay, so if it is a 70 degrees, what is the delta? It is 45 degrees up above the standard test condition. So the voltage will decrease by 18%. And therefore, the decreased voltage in absolute terms is 24.6 volt. And if you're, and in this you don't use the VOC, you don't use the open circuit voltage, you use the VMP rating of the module, okay, which is a little less than the VOC. So if it is, 250 volt is the inverter voltage, you find that it will take up to 10.16 modules to give the voltage, minimum voltage that is required by the inverter. But now you will not take the lower figure, you will take the 11 figure, because you have to give at least 250 volts to the inverter. So you can see that you will select a string must have minimum of 11 modules in this particular analysis. So you do factor these things in as you do your system design. Then of course, what is the size of wires? We did not cover the wires in the circuits that we were designing. You know, all these circuits, all these wires that are there, all the wires that are there. Okay, how do you select this? Well, this is first of all the current carrying capacity of the conductor is called the ampacity, and it is influenced by the thickness of the wire temperature, the insulation that is there for that particular wire, and the airflow around the wire. And if you are putting it in a raceway or a conduit which is reasonably open, then your current carrying capacity is that much higher. And if everything is very tightly packed together, then there is always a limitation which comes up because of that. So your aim is to minimize the power losses in the wiring system. Okay, and that means you normally, if you have a thicker or a shorter wire, it is good. You take due connection, care to build proper connections, prevent hot points, made good connections. These are all going to be in the actual practicals, what makes a difference. So we'll not cover it here. And typically you'll find in rooftop solar, they'll use 4mm or 6mm wire. And lots of people just go with the 4mm wire. It's cheaper. It costs you about 25 rupees a meter. The 6mm wire will cost 35 rupees a meter. but I prefer putting the 6mm up because you can't mix wire sizes on site, and it's better to use a little thicker one as it will be pretty functional. And if you're using for earthing, then earthing will go up to a far thicker wire usage, and it can be galvanized strip or use a thicker copper wire, and that is how you take your wire size. So you've got basics of the uh, system design covered in these slides for your reference. Okay, and are there any questions so far? So I will be uploading these slides onto my site www.india-inspires.com, and there is a section called Solar Excel where I put my solar related notes. This one will be available on the homepage itself, but you can also go to the Solar Excel site and refer it to there. Or since there are going to be downloads on this, you can also go to the downloads page and access the post from there. But it is what it is. So let me now give you a quick overview of the other softwares that are there. So I covered PVSys. You have, of course, had hands-on on Solar Lab. You've got a quick view of PVSys. Those of you who missed it, you can go to the YouTube site and select this for viewing. You can get it from the links. Let me take up SketchUp with Scala. So SketchUp, if you will have taken a look at it, you will realize it has a lot of rich CAD design features. That's the heritage of SketchUp. You are literally doing a CAD design with this. And while it is functional, it gives excellent CAD features, but it will lack some of the analysis that you would get from a software like PVSys or Helioscope or Solar Labs. Okay, so just for reference, uh, uh, typically PVSys is used along with a CAD software like SketchUp with Scala. So PVSys itself may cost you maybe when the dollar was lower, then it used to cost nearly 80,000 for a commercial thing, and then would grow beyond that in cost structures. SketchUp will be again pretty expensive when you start getting into the paid versions of it, and you have to use it along with other software that starts increasing your cost structures. Also, not everybody will find SketchUp with Scala that easy to work with. Personally, I love Helioscope and Solar Labs, and that's why I selected these as the software of choice. There are a whole lot of other softwares. I keep on repeating it. There's Helioscope, there's Aurora, Homer, Sundat. Really don't want you to worry about it. For example, found Solar Labs very functional and strongly recommended for the Indian rooftop solar design. And I will take you through another software which I really liked, Helioscope. On all this separate. This completes the 4th session of the solar PV design training for you people. Please you experiment. Please feel free to be in touch with me on any queries you have. And by and large, this is the starting point for your SPV journey. But you will go through a lot more as you actually do the hands-on on the site creation, the electricals, safety practices, and it will be a pretty enjoyable journey. Do work with the SSCI to create this wave in solar PV. The biggest challenge as of now is that people don't know, and they are doing very shoddy execution of the sites. And really speaking, it is not the quality. It's not the quality of the site of the equipment. It's also the design that makes the difference. The work that you do on the site makes a difference. Susan?
Hello, Ashwini sir.
After 20 minutes, I'll give you. So that's it. I have completed the session, friends, and look forward to your inputs. And I hand over back to the ESSC for developing the session for